welcome back to the afternoon session for today's topic in the summer school. It gives me great pleasure to introduce Dr. Zach Ulissi, and I'll give a quick introduction. But before I do that, Zach also happened to be the person who gave me my first talk in grad school in external conference. So it's a very small community.
You don't give away talks, you invite people.
Yeah. Invite me to my.
You say, thank you, Aditya, for giving a great talk.
Yeah, so Zach did his undergrad at the University of Delaware, and he has a very multidisciplinary background. So he did his undergrad in chemical engineering and physics, I believe. After which he did a master's in Churchill College in Cambridge, where he studied applied math and theoretical physics, and then returned to the US to complete his PhD at MIT in chemical engineering. After which he completed a postdoc at Stanford studying catalysis, related to kind of stuff he'll talk about today. After that, he started his independent career at Carnegie Mellon University, where he was for almost 7 years, I believe, before he joined fundamental AI research at Meta, formerly Facebook. I always mix up what the FAIR stands for.
It's not a coincidence.
Where he has been doing work on the chemistry team and is doing some cool work in AI for chemistry, which he'll tell us today in his talk, and then later also inform us more about these methods during the tutorial section. So with that, Zach, yeah, take it away.
Okay, super. Thanks for the intro. It's a pleasure to be here. Really fun to hear about all the cool things happening in AI for science. I don't know about you all, but this really does feel like a bit of a magical time. 5 years ago, it was still sort of on the increasing edge and methods are still sort of new, but now it's really fun that so many people think this is like a core part of their research. And I've also been really excited to see more and more of these tools go from like hypothetical research things that you could do to actual things that you use in the day-to-day to find discoveries. And I think that's really important because we actually want to use this to help ourselves, not just come up with fancy new computational methods. So first of all, everything I'm going to talk about has been a huge team effort. That's one of the really fun things about working in the space right now, especially at a place like FAIR and a university. So I'm not going to go through all the names, but just I did not do all the work. A lot of people helped. A lot of this work is also in collaboration with John Kitchen at Carnegie Mellon. If you've never met John, he is also super fun to chat with in the AI for science space, also cares a lot about data sharing and other things. So if you're interested in the academic side of these collaborations, feel free to reach out to John. And then I'll touch on some work that we've been doing in the metal organic framework space with people like David and AJ.
I just need to put the video on here, I think. I can see you. Go ahead. Sorry.
How about that?
Yeah, I see you.
Okay, excellent. Okay, so for the first half, I'm basically going to give some context on where I'm coming from, building large data sets, trying to make things more generalizable. I'm going to go through some of that because I think it also informs how I've been thinking about uncertainty, quantification, and active learning and things like that. When I started at Carnegie Mellon, as Aditya said, like 7 years ago, data sets were still relatively small. Like I was quite proud of the data sets we were built. We had like tens of thousands of calculations, but it was still very much in a, every time you work on a new project, you build the data set you need and you try and optimize for that sort of space. And if that's the way of thinking, then everything that matters is active learning, uncertainty quantification, know when you're extrapolating, stop right away, add more data. And what's been super fascinating has been the emergence of these large data sets and models that start to generalize in ways that were a little bit surprising if you had looked at this 5 years ago. And so that also changes how you approach uncertainty quantification and how you bet on different research methods in order to make this field move faster. As part of the invitation, they also asked me to discuss sort of the methods of uncertainty quantification. I'll try to keep that at a relatively high level. And then Daniel Schwabikolda is also super well known in the space. He's also going to give a talk on Wednesday. I think it's going to fit really well together because I'm going to talk a little bit more about what does it mean to get uncertainty estimates, and then he's going to talk about all the ways you can use them and abuse them and use them for data discovery. So it should fit in really well together. And then in the second tutorial, the second session, we have some live tutorials that I'll be able to show you some demos. You'll be able to try to play around with some of the code yourself, and we'll see how that goes. Live demos are always interesting. Okay, so whenever I go and give talks, usually one of the first questions is, why is Facebook Meta interested in chemistry? What's going on? this seems like a very strange world that we live in. Most of the things in FAIR are things like language models, Llama 1, 2, 3, vision models, segment anything, got a really big demo release last year. There's now a bunch of follow-ups to segment anything. Embodied AI is putting agents inside of robots. So trying to allow things to take actions in the real world. And then speech translation has also been a really big area. I don't know if any of you saw, but a few weeks ago, No Language Left Behind was a project that translates any language to any other language, including languages that are only spoken in the world. So trying to extend beyond English and German and Chinese to really anything in the entire world. No Language Left Behind was published as a Nature paper a few weeks ago, so that also got quite a big release. So FAIR is now fundamental AI research, definitely not Facebook AI research. One of the super cool things about being at FAIR is, on the whole, it's committed to open and reproducible research. And so what that means is, as a scientist, I really like it when I can go around and give talks like this and share our latest code and build data sets and release them to the world. And that's possible because the default culture at FAIR is open. One of the really nice things is also that we have access to really big compute. And if you think about industrial AI labs, maybe that's already sort of obvious. People like to throw around numbers of GPUs and things. But one of the things that was not so obvious to me was that there's also a ton of compute for building things like simulation data sets. And so I'll talk about some of those data sets, but basically we run on idle data centers in order to make those things happen. And some of the applications that I'm going to touch on are catalysis, direct air capture, and more recently, display materials for AR/VR applications. So this was really not obvious to anyone when we started this project 4 years ago on renewable energy, but Meta actually does care a lot about material scientists, and there are quite a few card-carrying chemists, polymer scientists, material scientists, optical engineers, people like that, specifically for AR/VR headsets and displays. And so if you think about a set of glasses that you might want to be wearing in your face, you want a really immersive field of view, you want it to be uniform, you don't want artifacts, you want it to be high resolution, really colorful, really bright. You want it to work outside if you're out in the sun. You want it to be lightweight if you're going to wear these glasses all the time. There's like a certain weight that you have to be below in order for people to be okay with wearing them. All of these are basically materials problems. So we want materials with super high refractive indices, low density, really tough, hard to crack. A lot of these are also very similar things to requirements that you might have for like a cell phone camera or a cell phone display. There's some overlap there too. And I'm just mentioning this because, again, from the outside, it was not obvious to me that Meta had a bunch of people working in material scientists, but that is actually the case. If any of you are interested in chatting more about that, I'm happy to talk after over the course of the summer school. So some of the work we do is internal on materials discovery. Most of the open external work is in renewable energy and climate. So things like direct air capture systems or taking CO2 and turning it into more valuable chemicals or water to hydrogen. These are all fundamentally challenges where we want to take one material and turn it into another. We need to be able to drive specific chemical reactions. We want catalysis to be efficient and not take a lot of energy and be cost competitive with everything else we have to do. These are also really, really hard materials problems. In order to make these things possible, one of the things our group spends most of our time focusing on is how to make these challenges. And if you go to the machine learning community and ask who wants to help with direct air capture or CO2 electrochemistry, a lot of people will raise their hand and say, yes, I want to do climate change or AI for climate. But in practice, a lot of those people do not understand exactly what sort of materials properties we're looking for or what sort of models would help. And so one of the things that we have to do is basically come up with benchmarks and other things that the machine learning people can compete on and contribute to so that they come up with models that are cool, and then those models are useful. So this doesn't happen magically. You don't just like throw a bunch of data online and all of a sudden someone solves your problem. This has happened because we run this website, opencatalyst.project.org. There's a live leaderboard. Anyone can submit here from anywhere in the world. We have a test set that we didn't release. I'll talk a little bit more about that. So if you want to get up on here, you have to predict on data that you've never seen before. It's all automated. You don't have to like ask our permission or anything. If you have a cool model, you just submit your predictions. It shows up in the leaderboard. And then at machine learning conferences like NeurIPS, we run challenges. So the past 3 years, we've had a Open Catalyst challenge where we try and come up with a new validation or test set and then ask people to try and build models. We have a little competition. We invite the best speakers. It helps to keep the excitement high. Another thing that's been really important to getting the machine learning community excited, and also touching on this idea that maybe we're going from small data to big data, is the availability of training data. So if you only have 100 data points, or 1,000 or 10,000 or whatever, you probably don't need the fanciest deep learning models. You don't need that many parameters. And so that's not to say you can't make an interesting machine learning challenge out of that, right? If you phrase it the right way, you can make that a really interesting mathematical computer sciencey sort of problem, but it takes some effort. And these things certainly get more interesting if you have a really large data set to fit on. You need to think about scaling, you need to think about expressivity, you start to think about generalization and scaling power laws and everything else that makes this field so exciting in the language and vision space. And so in order to do that, we've also been building simulation data sets. So we've had a few, including OC20 and OC22. OC is Open Catalyst 2020. These are basically little optimizations of small molecules sitting on heterogeneous catalyst surfaces. I like these systems. Obviously, I'm biased because I have a background in heterogeneous catalysis, so I'm going to tell you that these are the best systems. But these actually are sort of cool for the reason that if you want to do well in this challenge, you have to have models that work for small molecule organics, and they also have to work for solid state, and they have to work for interfaces in the combination and reactivity. And so from the external point of view, this does encourage you to be really good at building really expressive computational models for these atomistic systems because you have to involve everything. These are huge. So each one of these data sets has been order 500 million node hours of compute. If you went to AWS, that's something like $500 million per data set. We obviously don't pay those costs. The reason this is possible is because we run on idle metadata centers. When you're not using your phone to look at cat videos on Facebook, it's running on chemistry simulations for us. So super fun opportunity. And then, like I said, all of this is open source, commercial, non-commercial. You can do whatever you want with it. That makes it really easy for other industrial labs to also participate or other people to do startup companies in this area. We want this area to move fast. And the final thing, like I said, you can't just throw all the data online. You have to be super explicit about train validation test splits because you want to make sure everyone is comparing apples to apples numbers. And so if you go and look online, there's specific splits, and then there's no test set so that people can't cheat when they submit to the leaderboard. So these are not wildly creative. These are the same things. And I also like the first speaker today was talking about how you need to come up with benchmarks and leaderboards in order to get people excited about this area and help them make progress. These are the same sort of things that led to progress in the image and language communities. We're just doing the same thing for chemistry. In addition to OC20 and OC22, we've also had a data set on direct air capture, ODAC 23. So this was a slightly different system, metal organic frameworks, little molecules sitting inside. This is the sort of thing you would do if you wanted to come up with a fancy metal organic framework to selectively absorb CO2 versus water. I'm happy to go into the details. I'm not going to go into a ton of the use cases of these, but I'm happy to chat during the summer school if any of this is exciting to you. I mention this just because our models are increasingly generalizable outside of just computational catalysis. And so if you look at this picture and you say, this is cool, but my system is not this particular one, what do I do? Rest assured, we're trying to make these models work on many systems. If we can do it for heterogeneous catalysts and organics and metal organic frameworks, probably our models and the representations could be useful for your own applications if you're also doing some other atomistic system. Okay, and the last thing, all of this is open source. So in the second half, we will try a couple of demos. All of this is on GitHub. All the models are MIT licensed. You can do whatever you want. There's some educational resources for someone without a chemistry background. We have a live demo that I'll show. All of the data sets are available, including some others for specific validation applications like nudge elastic band transition state calculations or the replacement. And maybe just as crucially, and something that's gotten a little bit controversial, all of the trained models are also available. So that means everyone can benefit. You don't have to train your own thing from scratch. Anyone can go and use it as a starting point for whatever they want to do afterwards. So this is all very important if you want the field to move as fast as possible and let everyone help benefit. Okay, so that was just a little bit of background. I'll touch more on some of the details of these in the second half of the talk, but I'm going to switch gears and talk about uncertainty estimation and quantification. And one thing I just want to keep in mind is I'm coming at this from the perspective of someone who assumes that you're going to have huge data sets in your domain. and you're going to be building really large, deep models because that's the way that we all share data and representations together. And therefore, if we're interested in uncertainty estimation or quantification, we probably want to be working with methods and approaches that work with really deep, large models that are expensive to train in huge data sets, right? And that's not everything, right? If you really only care about small data sets and on the fly, there are other more sophisticated techniques for really, really small data problems. How many people already feel comfortable with uncertainty estimation, quantification? Very small number of hands, maybe 25%. Okay. That makes it valuable for me to be here. Perfect. Okay, so let's start with the basics. Why do we care so much about uncertainty? And this is hopefully pretty obvious. So the first is that as scientists and engineers, we need to know whether and how the models and the tools that we use work and whether or not we can trust them. And so as a bunch of people, I think majority masters and PhD students, right? You go and you give a thesis talk or some sort of committee meeting. The number one question is always going to be, what's the uncertainty, or how do you trust this thing? Or what if you use some other method? How would your results change? Like, that's just a really core part of who we are. We have to be able to answer this question, like, can you trust your results? And or should you be doing something differently? The second thing and it's sort of related, is these estimates also help us understand where we should focus our efforts. So we're all just people with 40 hours a week or 50 hours or whatever the number is to put effort into improving systems. And we could spend our time collecting more data or curating it, or we could make better models, or we could do more fancy analyses, or we could chat with our experimental collaborators more. These are all things that we should think about. But at the end of the day, we have a limited amount of resources. And so uncertainty quantification helps us understand, if we're making a prediction, where is most of the uncertainty or error coming from, or the biases? And maybe those are the areas where we should prioritize if we have a way to solve them, versus just saying everything in these complex systems we want to improve. Like, of course, in the best case scenario, all of my models and data sets would be absolutely perfect all the time. But this is the real world. That's not the case, right? Real world is messy. And I'm just showing this one on the right. I assume everyone's seen one of the IPCC reports, but I really like these reports because the predictions and projections they have to make are so aggressive and incorporate all the different possible sources of uncertainty, and they have to be so careful with how they represent that uncertainty in their prediction confidence intervals. It really is a really nice demonstration of how to do this explicitly when you can't collect data, right? They're making predictions 50 years out. They have to be able to come up with a confidence interval that is reasonable and hopefully useful, and also defensible, right? Because other people will certainly look at this report and ask, what about these other methods, or how do you know where to focus efforts? Okay, so also at a super simple level, I'm sure most of you have seen a plot like this as well. Most of us are exposed to uncertainty when we take a high school chemistry or physics or biology class. And usually it's in the form of, we're trying to measure something and we're talking about accuracy versus precision. So if we are not accurate and not precise, things are all over the place. If we are very precise, we are very repeatable, but we're doing the wrong thing. We have a bad step in our process. We're getting the wrong answer, but we're getting exactly the wrong answer all the time. We want to be high accuracy, high precision. We always get the right answer, and we have very narrow bounds. And of course, we could also be high accuracy and low precision. Like, if you take enough samples, you will get the right thing, and you're doing the right thing, but just your error bars are not as small as you might like to be. So that's on the measurement side. I'm sure all of you have seen something like this before. On the regression side, it's similar ideas, but different words. In regression, people usually talk about different sources of uncertainty. And usually the two that they break it down into are aleatoric and epistemic uncertainty. And aleatoric is basically sample-to-sample variation, just intrinsically within your data. There is some stochasticity or some randomness or something outside of your control, and that's leading to some uncertainty whenever you make a prediction. So in a region of low aleatoric uncertainty, these are all really tight. And high aleatoric uncertainty, these are in the right place and we have a lot of data, but there's quite a bit of scatter there. And then the other source of uncertainty is we just don't have training data near the points that we're trying to sample. And so in this intermediate region, we're going to have high epistemic uncertainty with whatever model we try and choose, just because there's no training data nearby. And this is important because it helps us get intuition on whether or not the problem is just, do we need more data? Or do we need to think about the representation that we're in? And those are the two that we're usually trying to trade off. And there's not one right answer here. Different sources of data, different data sets have different amounts of intrinsic uncertainty or clumping that could lead to high epistemic uncertainty. Now, it's really easy to draw a cartoon like this, but one thing that I think makes this really challenging right now in AI for science is that we basically are assuming that there's like some function that we're interested in and a single variable that we're trying to measure over. And so we draw a really simple cartoon, no problem. But the whole point of representation learning is in AI for science, or AI in science, or whatever you want to call it, is that we're trying to come up with fancy machine learning models that learn a representation on the fly that is more useful than the one that we started with. And more useful is usually something like it more smoothly distributes the data over some sort of manifold that we're learning on, or tries to unclump things, or tries to combine features in a new way that otherwise wouldn't have been obvious. And so we like to talk about, oh, we just need more training data, or, oh, something is going wrong as we move farther away from the training data. But when the representations are really complex, it's not always obvious if you're actually interpolating them on the data you have, because you may be in some new space where actually all the data is really nice and distributed, and you're making a prediction on something that is actually very similar to the prior data, even if it doesn't look like that just from a little picture of the structure you have. And so I'm mentioning this because probably everyone here is using fancy deep learning models and doing this, and it becomes really hard to then get intuition. I mean, we need to be careful in this space. Any questions so far? Feel free to stop, raise your hand, ask questions as we go. Yeah.
I'm just gonna ask for like your simulated training data sets, like how do you account for domain shifts to real data?
Yeah, that's a great question. So the question was, how do you account for domain shifts to real data in these simulated or computational data sets? And that's a super interesting question because there's multiple possible use cases of these simulations. So one is, I want to use a model trained on my simulations to predict some experimental data. And then the hope is that I discover some new catalyst or someone tests something, and I want an actual link between the things that I do in a computer and the things that happen in real life. So one domain could be like, I'm in simulation land and real world is not as simple as the systems that I'm interested in. And so that's one source of domain shift. That one's quite complicated. But the way that you generally solve that is you work with people who do better and better characterization, and then you try and nail down exactly what's going on. So you understand where the domain shift is happening or how you could try and improve your models. And the second source is we make some assumptions, like I show you a bunch of pictures of really simple things sitting on a surface, but then I move to some new type of reaction or some new heterogeneous catalyst active site that's not in the training data set. And I'm worried that it's not going to be the same as what's happening here. And that second one, it could be as easy as just collect more data on the fly and then see how well you're doing, or try and come up with some measure of how far are you from the original training data. But the representations, again, getting back to these deep learning systems, the representations are getting so good that more and more we're seeing that we can ask questions like, let's make a prediction for an entirely new type of heterogeneous catalyst that we've never seen before. And what we would have considered domain shift in the past is no longer a domain shift just because we learned a better representation. It's all mixed up together. These things learned how a small molecule works on a metal surface. And so the domain shift is no longer this heterogeneous surface to some other class of heterogeneous surfaces. It's all just organics interacting with metals. Does that make sense? Yeah. It's a little hand wavy, but hopefully that helps. Any other questions? Okay. Yeah.
You mentioned briefly that you're able to, the models are getting better at doing this,
Yeah.
pattern distribution. So, but how, especially for physical systems, how do you know that that they're predicting the right thing for the right reason? I guess in the field that you're working in, are there methods for verifying that the right precursors are leading to the right outcome as predicted by the model?
You're asking things like, how do you explain or how do you verify the models are actually learning the right underlying physics, or more just like
Yeah, yeah.
Yeah.
You mentioned like better internal representation.
Yeah.
If assuming that's true, then that means you're learning a better approximation to the underlying equations of motion. And that would mean that if you're breaking like a multivariate field, then the correlation between the different variables are also consistent physically.
No, it's a great question. So I don't know how to prove that one of these complicated models that does better on predicting physics that we care about is actually learning the right physics or the right representation along the way. You can ask some related questions. So I'm not going to go into it today, but like in computational chemistry, the models are usually really good at saying, is one thing better than another thing, especially if those two things are very similar to each other. And usually the methods are quite bad at just saying, what is the property of one thing, right? The is one thing better or worse than another is a much easier problem. And you get a lot of cancellation of errors in that case because you're comparing. And so if you're systematically wrong in both cases, that's still okay. So we've done some like really simple comparisons of, are we seeing similar cancellation of errors when we start to make those comparisons between computational chemistry methods and these machine learning models? And that would imply that maybe there's something about the representation in our fancy new models that's similar to the representation in the computational chemistry underlying methods. But frankly, I don't know how to like prove that. It's just like a observation that it seems like we're getting similar correlations. But if anyone in this room has an idea of how to like prove that these things are learning the right physics as we go, I'd be really interested in that problem. It's also an even more interesting question because whenever you start going to these really, really big systems, really big data sets, really large models, often you can make progress by simplifying the models and adding data augmentation and doing other things to make your model fast. And usually when you do things like that, you have to let go of something that you care about. Like the prior speaker was talking about quantization, and like I would love if everything was double precision, but like he was chopping things at a certain number of decimal points, and so he gave up a little bit of that accuracy in order to make things faster. You can do the same thing with fancy symmetries and equivariances and operations. Like there's all sorts of approximations that you can make. And so that intuition on like how do you prove that the model is learning the right physics in between becomes even more murky because you're like trading these things off. You say, I have a finite amount of time to train the model. So what do I do in order to make it fast enough and to work in practice? Does that make sense? Yeah. These are all super interesting open-ended questions. Okay, so one of the reasons that people love to think about uncertainty quantification is in things like active learning, which we heard about earlier. So a really simple example for Bayesian optimization or sequential optimization, whatever you want to call it, you have some sort of data, two black data points, you fit a surrogate model, something in between, you come up with some sort of acquisition function that says, what is the value of acquiring a new point? Maybe it's the point with the highest variance, highest predicted uncertainty. Maybe it's the one that maximizes or minimizes this function. Maybe it's the one that's farthest from the existing data points. There's all sorts of acquisition functions depending on what you want to do. You optimize this thing, you say one of these is the best over to the right. So you select a little X all the way to the right. And then you do this over and over. And eventually with a small number of samples, hopefully you find a really good point on the original function that you were trying to identify without explicitly knowing what you're doing. So how many people have seen an example like this before? Like Bayesian optimization is super common in a lot of like sort of intro stats or intro ML courses. Maybe 80%. These methods are super cool and they're provably exact as long as the approximations they're making represent real life. And so what I mean by that is inside of every one of these models is an assumption, something like a covariance function or a kernel function, there's lots of names for it, that says how correlated is a new point with a previous training data point that I had in the past. And so if your system happens to map to a covariance or a kernel function that you can write down simply in a closed form way, and someone has already written some code for it, you can do this exactly, and you get really cool results. But if that approximation that you just made, that this distance function is not actually the right distance function for your system, or the representation that you're using is not the best one, you have a problem. So whenever you use these methods, you should be thinking about what is the right distance metric. We're also assuming here that we had some sort of model that gave us uncertainty everywhere. So in this case, it was a Gaussian process with a certain kernel function, but there's many choices that we could have made there. Another thing that comes up, I'm asking you to optimize a new function, this red one. In one dimension, this is super easy. You just plot it out and you find the point with the highest one, no problem. Optimization in high dimensions is hard and stochastic. And so you can also waste a lot of time thinking about what the best point to acquire is if it's a really high dimensional system. And then the final thing that makes this a little tricky is it's on you as a scientist and engineer to say what is the right acquisition function. Because the acquisition function is really your like value system for life. Like, do I want my model to explore evenly everywhere? Do I want it to be like an equally uncertain model in all spaces? Do I want to just find the best answer so I can publish my paper and move on with my life? Right? These are all choices that you have to make. And there's not one right answer, right? It's on you to basically say, what do I care most about for my system? Okay. Another common concept, and this is really just going through words that you'll see, so you can go and look for papers afterwards and map these things and think about how to put it all together. In parameter estimation or uncertainty quantification, usually people talk about forward uncertainty, and that is basically I have some data or I have a set of parameters and I feed it through a model, and I get some uncertainty in the predictions, perhaps because the data has some bias, and if I selected a different set of data, I would get different results. Or maybe another reason is there are some parameters inside of my model that I actually don't know perfectly. I just have a measurement for themselves, and therefore I want to get uncertainty in the final predictions. So that's the forward process. And anyone who does design with these things talks about the inverse process. And that's basically, I have a set of observations and I have a model and I have some inputs that I think might be uncertain. And so given these observations, I want to try and predict the distribution of possible parameters that are feeding into my model or the input data. So this is also super common from your biology, physics, chemistry class, whatever. You have some sort of model of the world, some reactivity, some temperature dependence, whatever, and you're trying to fit those parameters as you do your experiments. If you're interested in this backwards process, the words to Google for are inverse uncertainty quantification. This is an entire field in and of itself, how to propagate backwards and forwards. It gets really interesting because often you're going from a single set of observations to maybe a whole region of parameters, and that whole region can have really interesting shapes and different design spaces. Okay, and the final thing that I think we should just be worried about before we jump into different types of uncertainty quantification is that as an AI for Science workshop, we're going to hear about all sorts of different methods and all sorts of different things that we can do. And so as all these things are coming together, our life is becoming more and more complicated. And so I would bet that 95% of you have a problem that somehow maps onto one of these blocks. There's different sources of data, literature, yourself in prior months, your lab mates from 3 years ago, some industrial lab, whatever, some real world experiments. We can do simulations. We mix these things together or choose our favorite one or do whatever we want in order to come up with some sort of fancy surrogate model. We heard about that this morning. Maybe we are trying to train generative models. So just something that is next token prediction, something like a diffusion model or a language model or something else. So these are ones that just try and map a random noise to a distribution that I care about, like pictures that I might see on the internet. We take these things, and again, this gets back to our job as scientists and engineers. We're supposed to be using these things to actually ask scientific questions. So that might be hypothesis testing. Is one material better or worse than another? Is my experiment working or not? Is there something else going wrong in my data? Do I actually understand what's happening? Right? These are all things that we should be doing. We can also be using these for predictions of decision making. Like I want to screen all the possible materials in the world, and then I want to pick the best ones and then try and make them, use them, discover new cool things. And then once you make these predictions or test these things, then you can iterate this loop and add more data through some combination of words like active learning, design of experiments, Bayesian optimization, inverse design. These are all different names for different fields that all do very similar things, just depending on which community you're in. All super, super interesting problems. And then even worse, in a lot of these, we're getting to the point where the models that we build also rely on these foundational representations. Someone else trained an image model that comes up with a really good image featureizer. And now we're using that inside of our scientific experiment by training a model on top of that. It's really hard to propagate uncertainty through every one of these blocks. So my point here is basically, like, there's nothing I can tell you right now that's going to say, this is the way to make the perfect set of error bars for your experiment or your data. I can't do it. The problem's too complicated. There's too many things going on here. The best thing that we can do is think about like what tools we have and ask what specific questions we want to do. And for any of these that you care about, go and try and quantify the uncertainty and be careful. Does that make sense? This also gets to the quote, all models are wrong, but some are useful, right? No matter what you do, it's going to be an approximation for the real uncertainty, right? The actual thing that's going to happen is like go out in real life and test your hypothesis and run the thing. And anything that is not just that is going to be an approximation. And so that's just something that we have to live with. How many of you are doing work that is not covered by one of these? Have I actually gotten a 95% coverage of the people in this room? I hear one. Okay, what are you doing? Okay, excellent. I want to hear. Okay, so let's talk a little bit about if we come up with a method to predict uncertainty, how are we going to measure, is it doing something useful? Because until we agree on that, it's hard to even talk about what methods we want to be doing. So the first thing is we want models to be as accurate as possible. No uncertainty whatsoever. Like if we're going to start combining models and different types of ways of estimating uncertainty, at the very least, we want a model to be accurate. So we normally make something like a parity plot, and we say if it's accurate, all the points are along the parity plot. And if it's inaccurate, maybe there's a bunch of scattered here, right? Super obvious. That's what we're all doing when we're trying to fit surrogate models. No problem. If you're doing heat maps or densities or whatever, we basically just want to squash this thing up against the parity plot. All of the figures and methods that I'm talking about are going to be from a paper and some work that I did with Willie Nieswanger. At the time, he was at Carnegie Mellon in the computer science department working with Eric Shane. Now he's a professor at USC. He loves nothing but like Bayesian optimization, uncertainty quantification. If any of this seems cool, you should reach out to Willie. He's awesome. And all of this is in a paper that we wrote together in 2020. So that's accuracy, no problem. The next thing that we care about is you're making a prediction on a confidence interval, and you want the actual data to fall within that confidence interval the correct number of times, depending on how you define your confidence interval. So we call that calibration. So normally that is on something like a calibration plot like this, going from 0 to infinity. And basically, we want the cumulative distribution of the experimental data, the residuals, to be similar to the cumulative distribution from our uncertainty estimates, right? That is, I'm putting bars on a plot. I want the actual data to fall within those bars 95% of the time if it's a 95% confidence interval. And I want it to work for 95%. And I also want it to work for 50% and 20% and whatever else I come up with. So calibrated uncertainty estimates, when you look at them, they will not always cover the parity line. If they always cover the parity line, that's actually not useful, right? But most of the time they will if it's a 95% bar, 95% interval. And if it's uncalibrated, you're going to get a model that is going to be making predictions for how long it is. And actually, that's not going to be super correlated with how far it actually is from the real ground truth. And therefore, you have an uncertainty estimate. It's probably better than not doing anything at all. But it's actually not useful in real life because you're going to be overly confident or underconfident in different cases. So we want these things to be calibrated like this. And that ends up with a curve that is very close to the parity line here. You can also measure the miscalibration area in one of these plots. That's basically the total integrated area between the parity line and this orange line. You want that number to be very small so that it is perfectly correlated, or sorry, perfectly calibrated. Okay, that's calibrated. The next thing, we want our uncertainty estimates to be as small as possible. So if you just have really, really big uncertainty estimates, first of all, it's going to be hard to ensure that those things are calibrated because they're all so large that it's a little bit hard to test, and probably you're going to have some calibration problems. But secondly, we want them to be as small as possible because we want as good of an estimate on the uncertainty as possible. We can't come up with a perfect estimate. If you can say exactly what is the residual, exactly what is the uncertainty, and that's exactly the residual, you might as well just make your model better. You can't do that. But for calibrated models, we want them to be as small as possible. And then the final one that comes up a lot, and this one took me a little while to wrap my head around. If you were making uncertainty estimates and you have some data, you can make a single prediction for the uncertainty for every single data point and always make it exactly 100% the same. And you can make it perfectly calibrated. So if 95% of the time your data falls within these bounds, and that's a fixed bound that you optimize carefully and you calibrate, you can get it to look really good on a calibration plot like this and report like a 0 miscalibration error. But this thing is actually not useful at all. Like, it's sort of useful to tell you that your model had some problems, but it's not actually telling you, are any of these points any more or less certain than others if I want to go back and revise them. So we also want these things to be as dispersed as possible. That is, we want a wide distribution of possible uncertainty estimates. And these are all three sort of heuristic things that we trade off in order to say, are these uncertainty estimates actually useful in real life? Any questions on these measurements so far? Yeah.
How would you balance like a wide predicted standard deviation distribution versus just having bad standard deviation?
Yeah, that's like, how do you balance the width versus the center of this thing? If I said I want it to be all the way to the left, but I also want it to be wide.
Yeah.
That's one of the things that gets quite tricky. So there's a lot of papers now that have compared a lot of different uncertainty estimates in different domains. I've written a bunch of my friends have written some. There's probably like easily hundreds, right? Probably more if you look at the entire computer science literature. And one of the things that makes this complicated is that whenever they do this, they will report a whole bunch of different metrics. And sometimes you get lucky and this, whatever the paper is about, this new method is uniformly better than everything else for all metrics. But often in practice, you're like trading a couple of these things off, and then it's sort of on you to say which one is the most important. So like, there's often some of the uncertainty quantification methods that are uniformly worse and you shouldn't bother with. But actually, when you get to things that are pretty competitive, like usually the papers I read are a little bit murky and saying that like some things are better for some things and some other metrics, but not like uniformly better 100% of the time. Does that make sense? Yeah. Okay. If you're interested in making any of these plots, Willie basically took the paper that we wrote together and then revised all the Python code to make it actually usable and put this all online in what he calls the uncertainty toolbox. It's basically a bunch of little tutorials and a really simple little Python library that helps you make these calibration plots and then do things like calibrate the estimates afterwards. If you have uncertainty estimates and you just want to make them better, you can systematically say, should I increase the error bars or decrease the error bars, or do it in some other way? And that calibration step is sometimes a little complicated, but this uncertainty toolbox will also help you with those too. So this is a case where you are overconfident, all of the error bars are too small, and I can just get a better model by multiplying all the error bars by some constant. And as long as I choose the constant correctly, this thing looks a lot better. Yeah.
Dispersion, do you have a countermeasure to that? I ask because sometimes we do see dispersion, but the small error bar are concentrated in one area versus the large error bar is concentrated on the other. So either way, you get dispersion, but then you're getting it in a very predictable manner.
Yeah, I think what you're saying is you have a dispersion curve and it's like extremely bimodal where there's one really sharp peak and then there's another one somewhere else. So there is dispersion, but actually it's not like uniformly and a whole bunch of points are clumped together, all sort of with the same error bars. I don't know how to like uniformly fix that. And this sort of gets to like, where are the sources of uncertainty in your data of like, are there actually 1,000 degenerate points in my experiment that are all the same, or are they actually different? But you could try different methods and see if any of them do not show that clumping. And maybe there's a different representation where all of a sudden those 1,000 points that are all getting mapped to the same uncertainty, all of a sudden become different in some way that the models can figure out. I'll hit on that a little bit more in a second on like different representations or different ways of doing this. Yeah.
I guess one puzzled me a bit is like, when you talk about this uncertainty quantification, they have like you have one data set, you build a model, and then you say, here I can on top of it with this confidence interval of you like more like a informal prediction type of perspective where you use like a say a third party.
Yeah.
So I'm going to use this one to calibrate myself.
Yep.
So I mean, you're just talking about in general, or you're talking more about?
I'll get to that.
Yeah.
Yeah. Ask the question again. But basically, just to repeat the question, it is, usually when you're doing these uncertainty quantification studies, papers, whatever, you try and get a set of error bars. Usually you're doing it for a very specific set of data and you provide some error bars. But whenever you do that process, one of the assumptions you're making is that the error bars work within the region that you calibrated this thing in, close to the data. But if you start to do something very different than where you came up with the uncertainty method, then sort of all bets are off. Is that a reasonable way?
Yeah, well, I guess it's more like to have your perspective on this talk right now.
Yeah. I'm gonna get to distance metrics and conformal prediction in a second. Okay, so these are just evaluation metrics. A couple of suggestions I would have. You can drive yourself crazy coming up with different models and different uncertainty methods. I probably wouldn't start this process too early until you already have a model that works. Like start with one that actually fits the data and then afterwards ask, how can I get uncertainty estimates? I also mentioned that because if your model is learning a representation that's useful for predicting a property, it's hopefully also learning a more useful representation for predicting is a new point similar or not similar to the training data. There's hard to guarantee that, but that's usually the case. And so it helps to come with a better model first. The second, and I think this also sort of gets to your question maybe a little bit too, whatever strategy you use here is itself a model choice. And so all the standard rules of train validation test split hold. You fit your models and whatever else you want to train data. You evaluate those on some validation data that you hope is representative of real life. Maybe that is choose 5% of the random data and ask, does my model work within the 5% of random data? Maybe it is choose a new class of materials that I've never seen before and ask, will my model extrapolate there? It is on us to say what is the right validation strategy. There's not one right answer, but that's on us as machine learning people. And then after you iterate this, you come up with whatever calibration strategy you want, you test it, and you try not to iterate too much on test, right? But again, there's so many decisions there, we just have to follow the same principles. And then the last one, I think as I said it a couple of times, there's not like one right answer here, but probably it's going to be on you to come up with different trade-offs, and I'm going to talk a little bit about some of the trade-offs in some of these methods. Okay, so I cannot cover all the different methods, but I just want to cover a few that I think are interesting because they are, I would say, compatible with these really large deep learning models. And we can talk a little bit about some of the trade-offs. So I've tried to roughly rank these from like ones that are really extremely model focused to data focused. So model focused, I mean things that are just like intrinsic to the model. Someone handed me a checkpoint. I want to try and understand what are the uncertainty, what are sort of the bounds of the confidence intervals that are going to come out of this thing. And on the data center, the data focus side, it's like, I really want to understand how close is my new data to all the previous things I've seen in the past. And based on that distance, I'm going to make a prediction on how certain or uncertain I should be. And one thing I just want to point out here is that if you believe the future is a really massive model that we are all sharing, trained on many, many, many different data sets, some of which might be petabytes in scale, like the previous speaker was talking about, or all of the languages in the world, or all of the images on Google, or all of the videos on YouTube, whatever you think is like the right training data, you're probably going to need something that's a little bit more model focused, because it's not going to be possible for you to get all of the training data, right? Like, even if you wanted to get everything, you could probably not download all of them onto one computer or one cluster. Like, it becomes a really, really, really difficult problem to ask. And so if you only have 100 data points, sure, like distance to the training data is quite reasonable, and that's a good strategy. But I'm just mentioning this because increasingly in my life, like it's becoming harder and harder for us to say exactly how far is all of our stuff from everything our models have seen in the past, especially when the models are getting trained on many different data sets at the same time. It becomes a really, really hard question. Okay, so the simplest thing that you can do, model ensembling. You take whatever model you think is awesome, and you just train it 3 times or 5 times or 10 times or whatever. Embarrassingly simple. There's many possible variations. You train exactly the same thing 10 times. You could bootstrap or choose a random set of the data every time to sample different models that could have come from different subsets of your data. That's another common strategy also in train validation test splits. You could leave clusters out. You could train on different architectures. Like I have my favorite machine learning model for chemistry, but someone else has a different architecture. Why don't I train both? And maybe if they're both working well, they'll agree. And if it's some nonsense prediction, they'll disagree. I could train a deep learning model and then collect a bunch of local minima as I train. So these are different like snapshots along the way. I'm basically bouncing around in parameter space, and I'm hoping the variation there is representative of the final variation. All of these are reasonable, and I'm sure there's a bunch of others that I haven't even collected here, right? There's lots and lots of ways you can come up with this ensembling. So a couple of the pros. One, the results for these, even though it's like embarrassingly simple, because you are sampling multiple models or multiple different sets of parameters, and those can be very different local minima in whatever your deep learning model is, these things tend to be very competitive. Like most of the papers are using ensembles as a baseline. And a lot of the papers that have been written recently are like, this fancy new method sounds cool, but actually it doesn't outperform simple ensemble estimates. That's not to say that you can't make progress in this field. It's just like, this is a really hard thing to beat. And so it's probably one of the things to keep in mind. It's also nice that it's so simple. Another positive thing is that because I come up with separate models for these different predictions, if I want to run a simulation with each one of these, I can propagate uncertainty all the way through to the final thing I care about by just running a simulation with each one of my models and then collecting an ensemble of the outputs of that. So from a like uncertainty propagation point of view, this is also a very natural way of doing things. So those are all the good things. A couple of the cons. So one, training and inference cost scales with the number of replicas that you're using in your ensemble. So for the models that I'm going to talk about in the second hour, it takes something like 1,000 GPU days for us to train with every one of those models. And it requires a pretty fancy GPU at this point with a small batch size with hundreds of millions of parameters. So I am decreasingly excited about training n copies of my models when they start to get very expensive. We can do it if it's important, but it's hard. And the other thing that's a little bit tricky is you're going to have to make an assumption on the number that you need. The right answer is probably going to be you increase your ensemble size until you converge your uncertainty estimates, and you find that you would not get a different answer with more. But that's not what most people do in practice. Usually they just do 3 or 5 and hope that that works. And so I'm just pointing out that it's going to be on you to do the right thing and converge that. And if you get weird results, sometimes it's just like you have 3 models and one is really bad. But if you did 5, you wouldn't get that bad one, or it'd only be 1 out of 5. This makes sense? Anyone have any, like, I'm sure other people have tried ensembling. Anyone else want to add something to this list that I've forgotten here? Okay, again, really nice, simple baseline. Second one. Another really simple thing I can do is I can train one model, and I'm going to ask it to, see if I can move that. Perfect. I am going to ask my fancy model to predict 2 numbers. One is the mean, and one is the variance on a new sample. And these models are generally called things like mean variance estimators or other things like that. I'm going to train my model to be accurate. And then I'm also going to train it to try and minimize the log likelihood here in this loss function. And the nice thing here is that usually I do this with just 2 different heads. So most of the model is the same, and then I have 2 predictions. And the pros of this is it's very simple, and it's the same training cost. Good. And I can include any known uncertainty because I can just train against this thing as well. But the con is it could be catastrophic model failures. If the model isn't working for the mean, it could also not work for the variance. Like those 2 things are not correlated, so you have a problem. And it requires modifying the training code and the architecture and the procedures. So you better have access to the whole model and be willing to retrain if you want to do this. Deep kernel learning, sort of similar. Instead of trying to predict a mean and a variance, I'm going to tack on a second model that uses the representation that was learned here. The pro, this model, often you choose one that has a pretty rigorous uncertainty estimate, like a Gaussian process, so you get all the benefits there. That's fun. You only have to train one model for the representation. And if you want to get the variance, you only have one forward pass. Those are all good. And a couple of the cons, it can be quite tricky to say what the right part is to use as the input here. I'll talk a little bit more about that in a second. And then some supplementary models like Gaussian processes scale really poorly with dataset sizes, so you have a problem if you still have 100,000 data points. And then finally, distance-based or conformal prediction methods. Basically, you try and come up with a distance metric. So how far is my new data point from the original training data? And the farther away it is, you say the higher the uncertainty. And the really good thing is that it lends itself to a really good visualization. Like you have this sort of map, you know exactly how far your data is, you have a really clear understanding of why your new data point is different. A couple of the cons, you have to have the underlying training data set. That was one of the things I talked about, or a representative subset. So it can become a little bit tricky to come up with those distance estimates. If you do this really naively, it's possible to make this really expensive. But there's also fancy methods like k-nearest neighbors or libraries like Base that can make this faster if you really want to go down this road. And similarly, sort of getting to your question, there's also potential for catastrophic failure. If you move far from the training data, all bets are off. All you know is that it's far. Okay. So wrapping up, I think I just have a few more. So there's a couple of challenges here. One is the latent space distance can be really tricky to define. And there might be things that you can do while training in order to make the distance in this latent space more representative of how far are you from the training data. So there's a whole bunch of machine learning and statistics papers in the space. And the second thing that makes this tricky in chemistry is it's not obvious how to do these when the representations themselves are equivariant vectors that are rotating around. And so I'm not going to go into the details of that, but Tess Schmidt is going to give a talk later on in the week on these equivariant representations. When Tess gives that talk, you should ask Tess, how do you define distance with respect to one of these equivariant representations? And it's a problem that I feel like someone's going to come up with a clever solution, but it doesn't exist as far as I know. Someone should do it. So this is representative of one of the models I'm going to show you in the second hour. Any one of these you can choose as a representation for your latent space for distances. It is on me to figure out which one of these is helpful. We also have a couple of papers that show how to do this for some of the models. I'm going to skip over this. Daniel is going to talk about how to abuse these estimates as much as possible. So I'm not going to touch that. The last couple of things I just want to talk about, there's stuff in between. So I can come up with systems where basically I share most of this and then I have a bunch of ensembles just in the output head. So I talked about these things as like either ensembles or something else, but there's all sorts of people trying to come up with strategies halfway in between. So this is a paper by Michele Seriotti that I really liked. Another one that I really liked is you can do similar things by taking these models and then trying to understand where in the simulation things are going wrong. I think Daniel's also going to touch on this with some of his examples, but basically you can analyze these things and say, systematically, this cluster, the model doesn't know what's happening, so let's rip it out and do a simulation there in order to fix it. Okay, so that's all I have. I'm going to leave with these questions, and let's take a half-hour break, and then we'll do some demos. Thanks.
Yeah, since we did some questions during the talk itself, maybe one or two questions, and we can take a break and second answer the question.
Oh, yeah, sure. That's fine. I'll also be around during the break too. Yeah.
Yeah.
I want to know that, how do you categorize Monte Carlo dropout? I see Monte Carlo dropout in one of your slides, but I don't know where, like, which, the four categories you just showed, some are more model focused, some are more.
Yeah.
So which one you would categorize?
So dropout is a technique when you're training these models, where often if you have a bunch of dense layers, you randomly drop out 5%, 10%, 20% of the nodes in your system. And you ask your model to basically make the same prediction or do a good job, even if you're randomly removing some of those nodes during the training process. And that's a really nice strategy because you can think about how to make things more robust and encourage the model to be useful, like using all of the different nodes within the forward pass of the network. In practice, most of the recent papers I've seen have not seen super competitive results for uncertainty estimation with those. So I don't want to say like it's not the right thing to do, but just it doesn't seem to be as useful as some of the others right now. And I don't know if that's like the dropout strategy or something else like systematic going on, but like it was really, really popular 5 years, 10 years ago, especially when it was all really simple, dense feed forward neural nets. In these more complicated ones, it tends to be a little bit more rare. But if I'm missing papers, also feel free to send me an email.
Really nice talk. So is it possible to predict algebraic and epistemic uncertainty separately?
Yeah, you can ask questions like epistemic of how far am I from the training data? That is well posed as long as you have a distance for that. So that one is relatively simple. And intrinsic sample to sample variation, a lot of these models you can also come up with, like in the ensemble case, you can ask your ensemble of models to make predictions on the training data. And often that will give you an idea of what that spread should be or what the validation should be. Like it can give you some idea of just how much variation there is in things that you know. But these are really just experiments that you have to do. I don't know of like a systematic, like this is the procedure to separate those out. It sort of depends on the strategy that you're using. Yeah, but it's not impossible, right? Yeah.
Yeah, I mean, when you should picture about, not having sampled some area at the beginning of the slides. I mean, you could also have like some assumption of the regular return the function that you try to estimate, right? Yeah, in this one, like the ground truth form that is very wiggly.
Yeah.
You can assume that, there's some kind of Lipschitz condition or this kind of things, and so you can try to use this kind of assumption to kind of refine your estimates. Is there anything like there's been machine learning to like, I know the type of function I'm estimating.
I like this paper is quite cool. This SNGP is basically them trying to come up with a representation that obeys the Lipschitz condition, and that's exactly the thing that they are trying to do. They're saying like there is something I want to do in my latent representation space that's going to make it easier afterwards to say what is a well-defined distance metric, and by thinking about that and then encouraging it with the right form of the loss function, you can make things better. And that's sort of like more smooth when you get farther away. So you can see these are little examples. Like this is correct. Whenever you get far away from the training data, you have really high uncertainty. That's good. And these are not correct, of like, these are sort of low uncertainty and or the uncertainty only goes out in certain directions. There's something wrong with the representation that was learned in that space. But this is an open-ended area. Short answer is yes, there are things that you can do, and that's why I like the paper.
Great, let's head to the break now, but Zach will be around and
Yeah.
we can answer the questions. Let's thank him.